apparently not drive. People didn't show up to the 120 notice.
Okay, well, they can watch the video. So. What I want to do is I want to finish up the white dwarf calculation. And then we'll start on tomorrow in class, we're going to then start the hydrogen atom. The hydrogen atom, just so you know, we can't go through the whole thing. So sadly, the phrase "it can be shown" will be a prominent feature of tomorrow's class. I'm going to have you do a couple of things with the daily homework so you can at least feel as if it's not entirely made up. Again, it takes about easily a solid 2 weeks of classes to get all the bells and whistles on the hydrogen atom. And we don't have time for that because through the whole class in itself for every detail will come out. Okay, so let's just do a little white dwarf stuff. So here, initially what we had is that we had our star, and then the composition of helium, hydrogen, and in the core is where the nuclear fusion is occurring. And so your hydrogen is converted to helium. And this is where our sun is right now. So you have gravity trying to pull everything together. You have nuclear fusion occurring in the interior. That's you're gonna have outward photons going out, outward pressure, and basically the gravity trying to pull this star together. And the inner pressure due to nuclear fusion, they're in balance. And this is called hydrostatic equilibrium. So our star is going to be in hydrostatic equilibrium for another 4 billion years. Okay, this is fine. But what's happening? That core keeps on becoming more and more enriched by helium. And eventually what's going to happen is that entire core becomes nothing but helium. At that point, there's nothing to prevent gravity from collapsing. So the helium core starts to collapse. And this here is some this envelope here is some of the hydrogen and helium. That helium core starts to collapse, the pressure goes up, the temperature goes up. If it goes up enough, you can actually start fusing helium. And remember, we call that the triple alpha process. And so what happens here is that now we have helium. Here we have some helium that hasn't fused yet, and then the inner part of that, we now get the helium going to carbon. And this is your triple alpha process. And notice you're getting this onion layer structure here. So what happens is the helium collapses the core, but it's only that inner part where you're getting the triple alpha process occurring. The outer part of the helium is not. What's going to happen? Well, eventually the entire core becomes carbon. Helium here, the whole core eventually becomes carbon. And then what happens? Nothing, no fusion going on. So the carbon core starts to collapse and then it magically stops. When it magically stops, we say we have a white dwarf. So the carbon core collapses, but eventually stops. And at this point here, this is what a white dwarf. This star is then called a white dwarf.
And it's still super hot from the fusing page.
Oh, it's still going to be, it's actually still quite hot, but it's going to be remarkably small. Anyone know how big, I'll mention this for the end, but anyone know how, all white dwarfs are about the same size or magnitude-wise? I don't know how big they are. They have the mass of our sun, but they have the size of the Earth. So when you look at what's called an HR diagram, that means something to you, or it may not. Don't worry about it if it doesn't. They basically, they're in a spot which means something really, really hot, okay, but also very, very small. So this is what we want to look at here. And we said, in all this process here, what have we been ignoring? We've been ignoring the electrons. And so what we're going to do, we're going to treat basically this interior of our white dwarf is basically a gas of electrons. And what's going to happen is that just like we did with the metal, and that's actually going to account for basically why this star doesn't collapse anymore. So it's a purely quantum mechanical phenomenon, which is preventing the structural. And what I want to do is show you that, and then how to calculate the radius. This is a beautiful calculation. Okay. So what we're going to do is this. The reason star doesn't collapse is due to the electrons that we have so far collected. Okay. So we can treat the electrons. It's basically like we did with metal. It's a free electron theory of metals. We'll just say free electron. So we'll treat the electrons as free electrons, like we did in metal. And this is going to actually work a lot better than you think something that's true for this would work. Yeah, turns out to work quite well. So let's try what we have for that and figure what we can do. Okay, before I ask people questions, which will be only you, Jay. Let me ask you, so how much astral stuff have you had? Okay, then okay. I don't get to harass anyone with questions. Okay. The morning stuff, the section on 120 was great because there was actually 2 more astral physics three, so I could harass them. Questions, but you're gonna pass. Okay, so recall. In the free electron theory, the we said the energy for the electrons was just 3/5 the number of electrons times the Fermi energy. And so this was really this 3/5 n sub e. Remember what this guy was, this h bar squared pi squared nf squared. I called this n max before, now I'm going to call it nf for Fermi, just because that's what it's probably called. Okay, over 2m L squared. So we're going to use the exact same thing for the electrons here. And it turns out to work really well. Now, when we did the metal, what did we assume the metal was? We assumed what kind of shape? Cubed. So the volume was what? L cubed. So what we said here is that we said that L cubed is the volume. The L is the volume to the 1/5 power. We're going to put this in here. This will be 3/5 n sub e h bar squared pi squared 2m. This will now be volume to the 2/3 power and s squared. Now this is going to be for a star. For a star, what will I put in then for the volume?
We're going to treat it as here.
Yes.
The volume was here.
Which is
4/3 power squared. Cubed.
Okay. So the volume we're going to say then is going to be 4/3 pi times the radius of your star cubed. And so what is that going to give me? Let's put this over here. I'm going to put a box around it because we're going to need it. So we're going to say the energy of an electron is 3/5 ne h bar squared pi squared and f squared all over 2m. I know that's 10, but I'm going to go to this 2m. Okay, what is this mass here?
Mass function.
That's mass of electron. Just remember that. We'll come back to that one. Okay, the volume is coming to the 2/3 power, so there's 4/3 over pi, so the 2/3 power. Now, what power am I getting R going to?
Square.
I would agree. Then I'm taking the cube root of this, That gives me an R, then I'm squaring it. So this is over R squared. So let's keep that here. So that's how the energy of a electron gas goes. So as my star gets smaller and smaller and smaller, what's happening to the energy of my electrons?
Going up.
It's going up. So this is going to cost gravity. Gravity is going to want to basically make this thing get smaller, but it's going to cost gravity. It costs it because actually the energy of the electron gas goes up higher and higher and higher. And at some point, it's the fact that the energy keeps on going up that's going to stop the collapse. Okay? And we're going to work it out. It's supposed to. Okay, so now let's write the energy of a white dwarf. So let's ask what is. Okay, so I'm just going to start saying white dwarf is WD because I'm tired of that. Okay, well, one thing we're going to add we're going to put the energy of the electron gas in there. Okay, with astronomy, what do you think this other term has to be? Just physically, what is it going to have to be connected to? You don't do anything in astronomy without this term. Gravity. Well, part of gravity. The gravitational potential energy. So we're going to have basically the gravitational potential energy for the object here. Now there's some other stuff too, and if you can put in more terms, but this is actually going to give us what we want. It's actually going to work actually really well. So we're going to basically put in the gravitational potential energy, so I'm just going to call it gravity. Okay, so this is going to be the gravitational potential energy. And now what I want to convince you of is that we will prove that if the star has a constant density, which it doesn't, but that's okay. This is still going to be actually a really good calculation of energy. Has a constant density, then this gravitational potential energy is going to be minus 3/5 G m squared over R. But what I want to do is I want to prove that. And I want to show you how the calculation goes. Okay. So everyone makes fun of the physics 1 and 2, and then why can't we do fun stuff? Because that's a really important class, those two classes. So what is the gravitational potential energy from physics 125? Okay, none of you had me, but I know this is always on what? That's only the gravitational potential energy near the surface of the Earth. But in general, what is it?
G times R times different R. No, those are masses. G times mass 1, mass 2 over R.
Very close. Okay. Put a minus sign under here. Okay. So what you have here is that this is M1. This is M2. This is R. The gravitational potential energy between these two is minus G, M1, M2 over R. Now suppose M1 instead were a spherical mass. And let's pretend that the mass is actually spherically distributed. What did Newton show? So if M1 were sphere of radius R with a spherical. Let's just say it has to be a radial distribution or spherical. I'll say spherical. My brain is falling apart, so I don't understand. The spherical distribution map. This is R. This is R. What's the Newton shell? What's the gravitational potential energy in this case? This is some big object here. Radius R. And the mass here is strictly your radial symmetry. Well, this is the origin of calculus. Yep.
Just treat it as a pointer or a point.
Exactly. You can treat it as if all the mass is at the center here, and you get the exact same. You get the exact same thing. Okay. Trying to work out gravitation, you basically have the gravitational force between two point masses. The Earth ain't a point mass. And so what did he have to do? He had to treat the Earth as a whole bunch of point masses. And that's how he ended up with developing chemical calculus. Okay, so that said, what we're going to do to calculate the gravitational potential energy of this is I'm going to build up the star by basically putting a whole bunch of little point masses together. We're going to have some little star here, some smaller radius. I'm going to keep on adding point masses to this until we get to the whole mass. And then once we have that, that'll be the gravitational potential energy of this. So what we're going to do is the following. Assume M2 is a small point mass. So I have this right here. So here's what I'm going to call this M, big M. This vessel radius, little r here. And this right here, this is my dm. And I want the tiny potential energy between this guy here, this guy here. So what would that be?
Minus G, M, DM, all over R.
All over it. Does that make sense? So if I want the total, what am I going to do? I'm going to keep on adding these DMs here until I can make my star out to radius big R. So if I integrate this, then that's going to give me my total potential energy. Does that make sense? So what I'm going to do here is, first of all, suppose, okay, so let's start. If rho is a constant, how can I write rho again? It's a constant. What's mass density? Engineers and physicists.
That's not everyone.
The mass over the volume, in this case, the volume is? Yeah, 4 to its power cubed. So your mass here, the capital, is going to be rho 4/3 pi cubed. Now, let's say this has a volume delta V. So volume of this dV. How do I write then the density of my little buddy dm?
DM over.
Done. So my dm is rho dV. So I'm going to substitute all these into my friend over here. So my friend, big M, is my buddy here.
Big M.
My buddy little d. It's really, and divide everything through my power. Does that make sense? Questions? Now, what would happen if instead of having a little dm here, I had actually kind of an onion layer of mass around here? So instead of having this picture, what would happen if instead I have this R? This is M. And then I draw a little onion layer here like this. This has a thickness dr, like this. What would happen here? I basically have the exact same thing here, but I have to have the volume of an onion. Because this will all have the exact, this all has the same R. So I can basically just put that value right there. Does that make sense? So what is the volume of an onion layer? This is an onion layer. Of thickness. GR around. Back to physics 126, another often maligned class. And then what would that be? What's the volume of an onion layer? And what does that give us? The surface area of the sphere, 4 pi r squared times the thickness dr. So what happens here is that this gives us du equals minus g rho 4/3 pi r cubed rho. Four pi r squared dr. So this is my onion layer. All over. If I clean this up some, I get minus g rho squared 4 pi squared over 3. And then I'm getting r to the 4th power, r to the 4th power dr. Does that make sense? Good. So if I now want the total potential energy of my star, where do I have to integrate from? Okay, a radius of 0. It's really tiny. I keep on adding on layers and it gets bigger and bigger and bigger and bigger. Out to a radius of bigger radius of the star. So this is going to give me u. Is going to be then this minus g rho squared. Let me write it down. This is minus g rho squared 4 pi squared over 3. But if I integrate this guy here, that just gives me this. That makes sense? And I'm going to write it like this. I'm going to put one of the rows here, 4 pi here, along with an r cubed here, over 3. And have that term. Now I have another row. I have another 4 pi. A sad little r squared. And then I'm going to pull the 5 out front. That's the exact same thing. I just rewrote it. Does that make sense? So why did I do this? Does this have a name? Absolutely. I think it does. So your density of the star, what do you know about 4 pi big R cubed over 3? Hey, what is going to be the mass times the density times the volume? It's going to be the mass of the star. This is M. Oh, this little fellow was looking sad. Okay. But I think we have 4 important math techniques that we use frequently. Hey, let's review the four most important math techniques, which are important. Hey, what are the four most important math techniques that we use all the time? In a clever fashion? No. Do not do that one. This is not one of the four clever math techniques. Okay?
You can 5 by 0.
Okay. What else?
Add zero.
Add zero in clever fashion.
Separation.
Separation of variables. Taylor expansion. Which one will we use here? One. How am I going to write this in a clever fashion? I'm going to write it as 3R over 3R. We'll say why? Well, I'm going to take this 3 and I'm going to move it out front. So this is my minus 3/5. Here's my G. This is my mass. I have this R in the bottom here. And I put this other 3 with this factor here, and the other R with this factor here. This gives me a density 4/3 pi R cubed. Okay, I think we have another mass term, and I think we're upset. So now we have minus 3/5 G m squared over R. This expression is used all the time in astrophysics and astronomy. It gives you really good estimates for the different things.
And does it work for all stars or just?
What was the assumption?
Density constant.
Density is constant, which is almost never the case, but it's certainly order of magnitude. Yes.
Is it supposed to be rho squared?
There, it is rho squared here. So I take one of the rows and put it here, and I put the other row over here. So this term here became the mass, and this term doesn't quite look massy. So this is why we multiply top and bottom by 3. So the 1R went here, making it cubed. This 3 went over here. Then I put out the other term of 3. Does that make sense?
Theoretically, could you kept one of them as just a mass the whole time?
No, because you actually need them both. Otherwise, because the mass is going to scale with the radius, you're not going to be able to integrate. So you have to write that all in terms of the radius. And the key is that the density is constant. So my colleague, Dr. Robinson, is teaching a course in cosmology. Guaranteed that equation is coming up somewhere. My colleague, Dr. Kendall, is teaching a course in star formation. Guaranteed this equation is coming up somewhere in star formation. I had to cash a check today. Guaranteed I had to use that equation when I cash a check. Okay? It's used everywhere. Gilligan's Island. Try watching Gilligan's Island without understanding this. But make Gilligan's Island incomprehensible. Okay? Try watching the Muppets. It's a metaphor for this equation. It makes so much more sense. Okay, so what do we have now? Let's look at what we have. We're going to use that equation. We can now say the mass of the wave, the energy of the wave, is my potential energy. Plus that incomprehensible expression there for the electron gas. So your 3/5 h bar squared pi squared 2m r squared here. Let's see the 4/5. 3 2/3 r squared here. And then your and we also need the number of electrons here. Now, this equation here looks like it could use a little bump. This seems a little TLC. Okay, we like this equation here because this is all in terms of what would you know about your white dwarf? Well, you know its radius and you know its mass. Well, you know the NF of a neutron of a white dwarf. Okay. How about the number of electrons on a white dwarf? It'd be really nice to write this in terms of the mass. So let's get this term here. Let's write this. And it's still gonna be R's in it, but I mean, I wanna clean it up, I want M's in there. I wanna get rid of the N sub E and I wanna get rid of the N sub F. Okay. So what do you know about the number of electrons in a star? What else does it have to equal? The number of electrons in a star has to also equal the number of.
Atoms times.
What do you know about the charge, electric charge of a star? It's gonna be neutral. So if you know the number of electrons, that also have to equal number of protons. You can say that the number of electrons equals the number of protons. Now, what is a star pretty much composed of?
Hydrogen, helium.
Hydrogen and helium. And hydrogen and helium, where is all the mass for the most part coming from for hydrogen and helium? From the nucleus. Okay. And what do you know about the number of protons and well, you may not. For the low mass nuclei, like helium, stuff like that. What do you know about the number of protons and the number of neutrons? They're equal. So everything's basically coming from basically protons and neutrons, all the mass. And what do you know about the mass of a proton compared to the mass of a neutron?
Mostly the same.
They're effectively the same. So how can I estimate them very accurately? The number of protons in a star. I give you a hint. The number will tell you. This is about 10 to the 57 for a sun.
That's easy.
It's not an accident that that's 10 to the 57.
It's, I mean, that means really sound garbage, but it's the number of protons and the number of neutrons.
Let's say I know the mass of the star. This is the mass of a star. Okay, what can I divide this by? Hold off on the 2 for a second. The 2 is going to be there. Let's get one factor, then we're going to get, but you're correct.
Grab that number of atoms.
What do we say all the mass is coming from?
Proton.
From the nuclei, which are basically protons and neutrons. They're equal number. If I took this and divided it by the mass of a proton or a neutron, because they're about the same mass, this would be the number of protons and neutrons. But what do we know about the proton and neutron number?
They're close to equal.
They're the same, so I have to divide that by 2 to get the number of protons.
Is there a neutron on the hydrogen?
Well,
Sorry.
there is a deuteron, and then there's 2 for a triton. There would be 26 of 12. That makes sense? So that takes care of this. Now, recall. What did we show that the sense of S value was? We called that N max before, so this one N max. What was this? This was actually 3 N sub E over pi. So what I can do is I can take that electron gas and I can convert it to something a lot more user-friendly. So I can say that this electron gas is going to be 3/5. Okay, here's my number of electrons. Yeah. I have my h bar squared. A 2m. Now, what is this mass here? Again, mass of electron. That's going to be important because I'm going to say something. I'm going to use it tomorrow. So it's 4/3. That's the set. 4 pi over 3 to the 2/3 r squared. I'm about pi squared. And what do I have? I have this thing cubed. So I'm going to write the 3 pi to the 2/3 separately. So this would be my 3 over pi, the 2/3. And then what do I have? I have then this guy here, the 2/3 power. Does that make sense? And just so you know, I'm gonna actually have to work out some numbers here. I really hated doing that, but again, it doesn't bother me now that I'm, a college professor. I hated it as a student. It's like, why are you doing this? You hate me. Oh, and now realize the genius of the calculations. Okay, but when you have a lot of factors like this in physics, what do? You call them a constant. So I'm gonna come over here. I'm gonna call this constant right here. This is, ooh, not that at all. I'm gonna call this constant right here. I'm gonna want that to be. I want the M and the R explicit. Then I'm gonna come over here. I'm gonna take all this here. All that there. And I'm gonna call that B. So this gives me B. M to what power?
Squared. Yeah, squared. No, not squared. True.
5.
It's
Over R squared. Okay. Now what do we have here? Now we have a nice expression, and I want to draw this out. And Dominic, this is the only first remove. Okay.
I'm not.
You're gonna say, wow, didn't we have this in class? So our energy of the white dwarf is going to be this minus A M over R plus plus B M to the 5/3 over R squared. Okay. Hey, I got to graph each of these terms. I'm going to plot the energy of the white dwarf. Versus R. Hey, what does this minus constant over R look like? It's gonna look like this. And so this is going to be this from here. That's my minus A M over R. Hey, what does this term here look like? Constant over R, positive constant over R squared.
That looks incorrect.
Okay, well, it's going to be something, it's going to be positive. It's going to go to fast, it's going to go to 0 faster because it's going as 1 over R squared. And it's going to blow up faster because it's going as 1 over R squared. So this is going to be, do this, it's going to be more something like that. Okay? This is going to be my B, M to the 5/3 over R squared. Okay, what would happen if I added these crazy terms together? I don't know. We might get something that looks like this right here. This right here would be the energy of the white dwarf.
Distance. So
Yeah, it looks exactly like that. It's actually the powers are different when you do like Leno-Jones, but it's exactly the same type of graph. That type of graph occurs absolutely everywhere. Okay. Where's going to be the radius of our white dwarf?
What? Do we lose an M squared for the A term?
Oh, yeah. Up here, everyone see where I screwed up? There's a square there. Sorry about that. That's actually would make a big difference. Sorry about that. Don't square up too. I dropped it down over there. Should be a square over here. I dropped it here, but more importantly, I dropped it here. Okay, where's nature? Where's my little white dwarf going to want to stay? What nature tries to minimize systems. Hey, you might want to live right here. Let's see if you're a little faster on the uptake than the 120 class. Hey, physicists and upper level engineering majors. Okay. How would you, what does that mean mathematically?
That's where the derivative equals 0.
Yes. Okay, so we take the derivative of this and set it to 0. Then I can solve for the radius. So if I take the derivative of this guy. So what's the derivative of up here? Okay. I'll be nice now. Copy down the constant form. Okay. It's like I did it for you.
That's R.
So what's the derivative of 1 over R?
And then it's the term negative over R squared.
Exactly. This has then minus 1 over R squared. Plus, let's do this term. Yeah, I'll copy down the constant. E m to the 5/3. Okay. Now what?
Negative 2 over R squared. I'm trying. Yeah, negative 2 over R squared.
That will be minus 2 over R cubed. And then we set this to 0. So the minus and the plus here, I take this from over here and make it positive. So this is A m squared R squared equals 2 B m to the 5/3 over R cubed. And take the R over here, the A over M over here. This will give me R equals 2 B over A. And you tell me what power getting R2 and M2. If you actually do the more rigorous calculation, you still get this. I'm going to 1/3 power in the bottom. So this is telling you that the R is going with this. Okay. Initially, that's a little on the counterintuitive side. If I had a really big, massive white dwarf, what would you naively expect about its radius?
Like that, it's very small.
Well, just in general, yes. But in general, if I were to tell you, if you didn't do the calculation, I have a big mass white dwarf, what would you say about the size?
Big
It
radius.
says bigger. Okay, what is this telling you? It's actually smaller. Now, what's going on physically? We now understand. Because what happened, if it's more massive, what do you know what the gravitational attraction is? It's greater, so it can actually squeeze this thing together. But then what happens? If this gets smaller, this energy here, since it's going as 1 over the distance squared, actually increases quite a bit. And at some point, then it's going to balance each other here, and you're going to have your white dwarf. So if it's bigger, there's more gravity, it squeezes the star, but then eventually, because of the electron pressure, it stops. Okay. And again, if you put in the values here, it turns out that the size of white dwarfs are about the size of the Earth. Okay. And that's how they will live. Eventually, that carbon core cools, and what do people think the carbon core eventually becomes? A giant diamond. So you get this enormous diamond basically in the center of these, which is kind of amazing. And the cooling rate for these things is ridiculously slow. Ridiculously slow. And so, good luck getting anything. I don't recommend trying to mine it. Don't take your mining equipment to a white dwarf. I'm going to get a big diamond. Bye. Good luck.
I wonder if it'd be crystalline, if it'd be amorphous. Probably.
If it's a crystal, we're not doing it. You probably just, my guess is it's probably a single crystal, but I don't know. Yeah, but as you get further out, my guess would probably be a little graphite. I don't know. Don't honestly know about the interior. The conjectures that would be eventually would become a diamond, which is kind of cool.
What happens to the rest of the gases that don't get used? They just kind of fly off.
Well, okay, so remember what we mentioned last time is that once that core becomes all helium, that helium core starts to decrease. It loses gravitational potential energy, which goes to the outer envelope, and that expands. That's the red giant. And so you have some matter that's still left out here. And then what happens? Then gravity pulls the thing together. Just still matter left out here that still hangs out there, and that's your planetary nebula. So if you look at the Ring Nebula, which is one of the few things I can actually find in a telescope, it's pretty good actually. That's actually an example of a planetary nebula. But you'd sub here. Now, suppose instead the star is more mass. So our star is puny like our sun. This is going to be the end stage of our sun. It's going to be more. Now, if you had a more massive star, what would then happen to the carbon core? The carbon core, if it's more massive, continues to basically compress. Then what happens? Yeah, the carbon core fuses to other elements. And when does the fusion stop? Iron. Because basically, if you fuse iron, you don't get more energy out of it. It actually costs energy, so the process stops. Now,
does it completely stop, or does it just decay instead?
no, it actually stops. And then what's preventing gravity from collapsing the star?
Pressure from the fusion.
Absolutely nothing. Okay, so now what's going to happen is that everything is coming together. And so remember what happens here. Now, remember before I mentioned you have a neutron, and they can go to a proton, and it's electron. And then to a neutron, that's the decay process here. What happens is in these stars, when they all start to collapse together, you have the inverse process. You have protons interacting with electrons going to neutrons, and then electron neutron. So what's happening? Your star is becoming more and more enriched with non-neutrons. The remnant that's left is then called a neutron star. And what's going to happen here? Damn it. Okay, well, and this guy here, this B here. Okay, remember how I'm pointing out the mass of the electron here? Now we're not going to have basically an free electron theory. We're going to now have a free neutron theory. So that mass would be the mass of a neutron. Now, how's the mass of a neutron compared to the mass of an electron?
Very large.
It's about a 2,000, almost, it's like 18, I think it's like 1,830, oh, 2,000. So basically what's going to happen to our little star here? Our little neutron star, basically we're going to have this value here divided by a factor of 2,000. If you take the radius of the Earth and divide it by a factor of 2,000, what do you get? You get the size of a city. So a neutron star would have the mass of a star, but the size of a city. Okay. And what happens is that all the matter collapses together. This process occurs. You basically have the neutron star left. It's very hard to compress nuclear matter. My advisor got into, because my background is in nuclear power. My advisor got into this extended debate on the compressibility of nuclear. This is called nuclear matter. Actually, it's not nuclear matter, but of neutron matter. My advisor thought it was fairly incompressible. This other guy, I think, was probably wrong. Thought it was fairly soft. You can't compress it much more. So what happens? You have all this infalling matter. Can't compress this anymore. That creates a shock wave that goes out. That shock wave then obliterates your star. Again, that's your supernova.
So you'll have this neutron-rich core in the center, and then the elemental, it's stuff that's still elements on the outside.
No, that all gets basically dumped out in the supernova, and that's basically forms your planets and everything else.
No, that was my remaining question. The elemental stuff is stuff that gets blown off.
Correct. Okay. And that gets a lot of the periodic table. What happens is it gets a little more complicated, and the calculations are less clear. So what happens is, how do you get, that'll get you up through iron. So where the rest of the periodic table. Okay, they're thinking the process here that what happens is you'd have these, well, you'd still have some nuclei going out, and they would absorb neutrons, and then those neutrons then decay, then they sort of, you get the other elements. They're called R and S processes, rapid and slow processes. If you take the course in stellar formation, not stellar formation, stellar structure, you'll actually go through and work out those. The stuff is beautiful.
Is that graduate level or is it undergraduate?
What?
Is that graduate level or undergraduate?
It's an undergraduate level, but you can do a lot. I had a whole course in grad school. Actually, I had the guy who taught me was the guy who did some of the initial computer models for it. Very nice man, the most incoherent teacher I've ever had in my entire life. He got in there, and we're taking very first day. It's a course in basically stellar structure. He started talking about dredge up and these stars. These asymptotic giant branches stars with dredge up. This went on for like 2 weeks. We had no clue what was going on. Then at some point he just had these overheads, and he stopped and went, "Is any of this making sense?" He went, "No." He went, "Oh." He went, "I never could get to this point when I teach the class, so I thought I would start here." And he went, "Would you like me to start at the beginning?" I was like, "Please." I'm like, "Okay," but it really felt good to kind of start here. And that was the whole class was like that. It was utterly incoherent.
That sounds like something that'd be funny to do in the first 5 minutes of the day. Let's go for 2 weeks.
I mean, he was a very, very kind and decent, but an utterly incoherent teacher. The whole class was. There was one time he was very proud because he had this one derivation for something, and he didn't remember anything. I went, "I think that looks like Fermi's golden rule. You did blah blah blah." You go, "Yeah, that's what I did." Not a very kind man. Okay, we're done.
You study all this in lecture four and you just